In this video we're going to work through a past paper question which brings conic sections and discriminant together into one question, along with some transformations as well. It's actually going to be a translation to the ellipse. Okay, so it's a fairly long question. Maybe pause and have a little read through it first, see what you can interpret from it. And we are given an ellipse which is called E, which is x squared over 5 plus y squared over 4. Notice it's clearly an ellipse because it's a plus. In the last video we saw a hyperbola which was a negative. Subtle difference, but an important difference. There's a line L, y equals x plus 4, so thinking about that line there, it's got a gradient of 1. It's going to go through there at 4 and there at minus 4. And the first part of the question just wants us to find the coordinates where the ellipse intersects the axes. Then we're told the ellipse is translated. And if you look at this vector translation, it's translated in the x direction, so we're going to be moving it along in the x direction. If p was positive, we'd move it that way in the positive x direction. If p was negative, we'd move it that way in the negative x direction. We then get asked to set up this equation, which is for the translated ellipse and the intersection. So obviously when they intersect, we're thinking simultaneous equations. The reason why, if you ever get a question that looks like this, the reason why they want you to set this up, if you notice, it's just a quadratic. So there's A would be 9, B would be this, and C would be this. And then we're asked about it being a tangent, which is where the discriminant comes in, but we'll see that a little bit later. Okay. So for part A, there's a couple of ways of thinking about this. If you want to compare it with the general form, it would be over root 5 squared and over 2 squared. So therefore, it would cross at root 5, 0, minus root 5, 0, 0, 2, and 0 minus 2. That's just from comparing it with the general form of an ellipse and remembering where it crosses, but you don't need to overcomplicate this. You could also do this if you didn't know anything about ellipses, because you just need to realise when something crosses the x-axis, what do we know? Just like any function, if any function crosses the x-axis, that always happens when y is equal to 0. So you could even just look at the equation and say, oh, y is equal to 0. We're solving x squared over 5 equals 1. If x squared over 5 equals 1, x squared equals 5, x equals plus or minus root 5. But obviously if you can just remember this, it saves yourself a tiny little bit of time. Okay. So next part is quite quick, I could probably fit it in here. If you translate the ellipse with this vector, remember that you're replacing x with x minus p. So that would just be x minus p squared divided by 5 plus y squared over 4 equals 1. Okay, so let's read part C carefully. And it says, show that if the translated ellipse, so this is our translated ellipse, intersects, which is where we do simultaneous equations. So for part C, what we're aiming to do is when this translated ellipse intersects this line here. And if we just pause and think about that for a second without getting lost in the algebra, like if you just look at this, you should be able to just try and visualize that P is going to be negative. Like clearly the answer I'm aiming to get here is we're going to move it to the left. And there's one version where you move it a little bit. And I don't know, maybe just pause for 1 second and see if you can figure out when the two possible situations are where it intersects. With it being a tangent, I should say, sorry, if we're thinking about the two tangents, which comes later. Okay, so what we're going to end up with is the line. The ellipse could be there, and it could just touch it there, but you could also have the line, and the ellipse could move further that way, and end up being a tangent. These are clearly separate diagrams. Terrible sketch. But there's going to be two situations where you get a tangent. One where it just touches there, and then if you keep going, it comes through and touches it there. Okay. Importantly as well, I sort of skipped over this, but when it's a tangent, the line and the curve only intersect once, so that is your key to think about the discriminant. I mean, there's two main things. One, you've got this equation set up, which is perfect for the discriminant, but two, if you think about the tangent, there's only one solution, so we need to interpret that as the discriminant would equal 0, so we get one solution. Okay, so we've got x minus p squared over 5 plus y squared over 4 equals 1, and the line, which is y equals x plus 4. Clearly the easiest way to do this is to just replace y with x plus 4. Also, looking at the equation that you're aiming to get to, the y has been removed, so when we do simultaneous equations, we're aiming to remove the y. Something else I'm going to do, I'm going to multiply the whole equation by 20 just to avoid the fractions. I don't want any fractions. The answer's not got any fractions in. If I multiply by 5 and 4, it's the same as multiplying by 20. So that would be 4 lots of x minus p squared plus 5 lots of, multiplying by 20, the 20 over 4 is the same as just multiplying that one by 5, isn't it? Y squared, so to use a bracket, y is x plus 4. Don't forget to multiply the whole equation by 20. And then all we've got to do is expand this out, and we should get to this answer here. Oops, that's not right. Minus 2bx plus p squared x squared plus 8x plus 16 equals 20. Always good to look at what you're aiming for as well and sort of make sure you are getting to that, and you can even use that as a guide to help you with the last couple of steps. But clearly we've got 9x squared. If you group the x terms together, it wouldn't look exactly like this, but we've just taken a factor of the negative out, so maybe just leave it like that for now. Minus 8 px plus 40x plus 4p squared plus 60. And obviously just justify the answer by making sure you write the final answer that you're aiming for. So they're taking a factor of x out, take the negative out as well. Minus minus is the same as the plus. Okay, for part D, as we said, we've already interpreted this, but just to recap, if the line is a tangent, it means it only touches it once. If it only touches it once, this equation here, this equation represents the intersection between the ellipse and the line. So if this equation's got one solution, the ellipse and the line intersect at one point. Okay, so tangent b squared minus 4ac is equal to 0. When you square the negative, you could actually just completely ignore it, but if we are going to, my preference actually would be to not write it like this. I think more people make mistakes. I'm going to think about it as minus 8p plus 40, because that is the same as b, isn't it? Minus 8p plus 40, and then if I square this, I don't have to worry about the negative and the bracket being squared. Minus 4 lots of a, which is 9, plus c, which is 4p squared plus 60. Set it up as an equation equal to 0 because we're aiming to solve this as well. Okay, so I've just expanded this out, and we ended up with 64p squared minus 640p plus 1600. Be careful with the negatives here. Minus 144p squared minus 2160. Tidying this up, I noticed that I could divide everything by minus 80 to give me this relatively straightforward quadratic p squared plus ap plus 7, and we can factorise that to p plus 7, p plus 1. So we haven't actually finally answered the question. We'll come back to what the question was asking in a second, but let's just think about what that tells us. P equals minus 1 p equals minus 7. If we think about the diagram, we can see that if we move it to the left by 1, it's going to be a tangent. And if we move it to the left by 7, it's going to be a tangent as well, which is the translation. What we're actually asked to do, it says find the coordinates of the points of contact. So we know what the translation is, but we actually need to figure out what the coordinates are. X and Y coordinates, it says coordinates of the 2 possible points. There's still a little bit more work to do. What we can do now, if we know what P is, and you should remember this from when you were doing rational functions and discriminants, the key to unlocking these questions sometimes is to actually come back to this question here, to this thing that you've set up. Because if we sub in the P values, with rational functions it was the K values, wasn't it? But if we sub in the P values for this, that's going to tell me what the X coordinates are for the intersection point. So if we start with P equals minus 1, that would give us the quadratic 9x squared minus, so if P is minus 1, that would be minus 8, minus 4, minus 48, minus sub plus 48. P is minus 1, so that would become plus 64 equals 0. And again, if you remember this, there's only one solution, don't forget it's a tangent, there's one point of contact. So although there's 2 P values, there's 2 different points, but each of those equations should give us one solution. And you should see that this same thing happens with this equation. We get a quadratic, which we can factorize into a single bracket. That's just going to be 3x plus 8 all squared. Like, I didn't even really focus on it, I just looked at the 9 and the 64 and put 3 and 8. But let's just check, like if you expand this out, 24 and 24, 48, it does work, doesn't it? So the x coordinates, because we knew there was only going to be one solution, so that only comes from when you get a repeated root. So x would equal minus 8 over 3. Now we just need to figure out what the y value is. You might be tempted to go here, but don't forget, this is a point on the ellipse, but it's also a point on the line. So easiest to figure out would be use the line to figure out what the y coordinates would be. So y would equal minus 8 over 3 plus 4, which is 12 over 3. So 1 point would be minus 8 over 3 brackets 4 over 3. Maybe pause and try and do this similar technique to find the other point when P is equal to minus 7. Just to clarify as well, just check that that makes sense. Like if you move that ellipse there to that point, you can clearly see that the x coordinate's going to be negative and the y, that we were expecting a positive y coordinates, which is what we've ended up with there. Okay, nearly there. So if we sub in minus 7 into the same equation, we get 9x squared plus 96x plus 256, which looks like it's a bit of an awkward quadratic, but just check, we only want one solution. And both of these are square numbers, aren't they? That's 3 squared, 256 is 16 squared? Yeah, 16 squared. So x would equal minus 16 over 3, therefore y would equal minus 16 over 3 plus 4, which is 12 over 3, so y would equal minus 4 over 3. It's so nice the way this question fits together, isn't it, and the numbers fall out like this. Just to refer back to the diagram, you might have been able to see that that was minus 4 over 3 just by thinking about what I spoke about earlier. If you move it that way and it touches it, that y coordinate we knew before was 4 over 3, wasn't it? So you can see that when you move it further and it touches here, it's hard for me to draw it, but when it touches there, you'd argue that clearly, due to the symmetry of the ellipse and the line, you could see that if that one's 4 over 3, that one would be minus 4 over 3, wouldn't it? So you might be able to just infer that without doing the calculation. But the answer would be the other point would be there. Okay, thanks guys.